So now we're going to talk about homogeneous linear systems. So if we look at the matrix equation AX equals B, where A is a matrix and X is a vector and B is a vector, we say that the system is homogeneous if this B vector is equal to the zero vector. So if it's homogeneous, it's the system AX equals 0. And if it's non-homogeneous, then it's AX equals B where B is not 0. So what we need to remember about homogeneous systems is that they always have a solution. If I plug in the 0 vector for X, then a matrix times a 0 vector is going to be the 0 vector. So this is always a solution. So X equals 0 is what we call the trivial solution. It's the obvious solution, okay? Now, can you get a solution that's not equal to 0? Well, it depends. So let's look at a matrix. If we augment with the 0 vector, and we've got, whatever the matrix is here, A, this is A. If you do row operations, right, there's only 3 you can do. You can switch rows. If I switch rows, you're switching a 0 with a 0, so those are going to stay 0. If you multiply a row by a constant, you're multiplying 0 by a constant, you're going to get 0. If I add a multiple of 0 and add it to another 0, I'm still going to get 0. So this column of zeros will not change. And that's true in anywhere in the matrix. If you get a column of all zeros, there's nothing you can do to change those at that point. They will remain 0 until you're done. So that also tells you why you can't get a no solution, right? To get no solution, you have to have all zeros on the left and something non-zero on the right. And these are already 0, so you can't get a no solution. So these are always consistent. So when am I going to get something that's not trivial? So let's say we, I'll just make this a 4x4. If my matrix system reduces to this, where I have a leading 1 in every column, then the only solution you get is the 0 vector, right? So if there's a leading 1 in every column, then the trivial solution is the only solution. So what would you have to get a non-trivial solution? You would need a column that does not contain a leading 1, meaning you need a free variable. So if you have no free variables, that means the trivial solution is the only solution. If you do have free variables, I guess we should say, let's say at least one free variable. If you have at least one free variable, then there are non-trivial solutions In fact, you have infinitely many. Now you still have the trivial solution because the trivial solution is always there. But if you have a free variable, you can get non-trivial solutions. There will be infinitely many of them because you can let that variable be anything. because you can let that variable be anything, you can get a solution that's not just 0. So we're going to solve the following system. Are there non-trivial solutions? I'm going to put this in my calculator. Double check it, make sure that I put that in correctly. Looks like I did. RREF. So this system, and I'll just write it all out here. The system reduces to this, according to the calculator. So because this has a free variable, we can get non-trivial solutions. So the answer is yes. Now if we want to know what those are, you solve it. So x1 looks like x1 is 4/3 x3, x2 is 0, and x3 is itself. So as long as I let x3 be something that's not 0, then I will get a non-trivial solution. So for instance, if I let x3 be 3, then 403 is a solution. So if we have a non-homogeneous system, we can compare that to the homogeneous system and see what would happen. So we're going to find solutions to ax equals b, and we're going to write the solutions in parametric vector form, and we're going to compare them and see what they would look like. So I'm going to start with the non-homogeneous. Whoops. It's like the same matrix we had a minute ago, so it should be easy to put this in. -7, -1, -4, we get this. So I'm just going to solve it the way we've been solving it. So x1 would be 4/3 x3 minus 1. x2 would be equal to 2. And x3 is itself. Now for parametric vector form, what does that mean? So we're solving this matrix equation, and we're solving for the vector x. So we're going to write x the vector x as this. And we're going to kind of decompose this vector into different parts. So the first part is I'm going to make a vector that just has x3's in it. So anything that has an x3 is going to go in this vector. And then plus, the last one's going to be anything that's just a constant. So I've got -1 here, 2, and 0. If you see, if I add these two together, I'm going to get this vector, right? If I add this vector and this vector, I'll get the original. So I just took everything that just had x3 in it and everything that had just a constant, and I split those up. And now I'm going to factor out this x3 like it's a scalar. You see I've got two vectors, x3 times this vector and plus a constant. So this form here is called parametric vector form. Now if we go back to the homogeneous system, what would be the parametric vector form here? So x would be, I don't know why I put a negative there. Four-thirds x3, 0 x3. There's no constants, right, to pull out. So this is just x3 times 4/3, 0, 1. So that's the parametric vector form for the homogeneous system. So let me write that down. So for ax equals 0, x equals this x3 times 4/3, 0, 1. You can see that our non-homogeneous system contains that solution, right? So this part is the solution to ax equals 0. And it's got this plus -1, 2, 0. So if I look at this, let's look at the homogeneous system solution first. I'm multiplying any scalar times this vector. And, you know, if x3 can be anything, so the solution is the same as the span of this vector, right? The span would be all possible linear combinations of this one vector. And we've already seen that if you span a single vector in R2 and R3, this is just a straight line. So if that's a straight line, then what is this? This is that straight line plus this constant. So this ends up being a straight line parallel to this line. So it's like the line that you get with the homogeneous system solution, and it's been shifted, right? So this is a shift. And where is it being shifted? It's going down 1 in the x direction, up 2 in the y direction. It's staying put in the z direction, right? So we have a span of a vector, gives us a line. And then the non-homogeneous system, you get that line, and then it's been shifted, so you get a straight line that's parallel to this one. So that's kind of the geometric description of these. Now, if you're in R4 or R5, you can't really talk about the geometric representation, but in R2 and R3 you can. So let's look at this system. It's just a single equation, right? So I guess we need to say system in quotations, right? quote unquote system, we're just going to solve it like we would any other system and write the solutions in parametric vector form. So it's just going to be a matrix with one row, and we're augmented with 0. And all I've got to do here is divide everything by 10. And I'll reduce that. So it's got 3 variables, x1, x2, x3. x1 has, the x1 column has a leading 1. These two do not. So they are free. So we have in our solution x2 and x3 are free. x1 is 3/10 x2 plus 1/5 x3. So we want to write this in parametric vector form. So what do we do when we have 2 free variables? I don't have a constant here, but I can split these up by their free variable. So I'm going to put everything that has x2 in one vector and everything that has x3 in the other one. And then we're going to factor out those free variables like they're scalars. And we get this. So what is this? We have weights x2 and x3 multiplied times these vectors. You know, this is a linear combination of these two vectors. And because we can let x2 and x3 be anything, this is really all possible linear combinations of these two vectors. This is the span of these two vectors. Which means this is a plane in R3, right? But this is the parametric vector form. Okay. So when you have 2 free variables or more, you're going to split up, you're going to decompose your vectors, split them up by the free variables. You're going to put all the free variables in one vector, all the other free variables in another one, right? So all the x2s go in the first one, all the x3s go in the second one.